We present our paper, Variational Relational Point Completion Network. Real scans for 3D objects are often sparse, noisy, and incomplete, due to sensor limitations, occlusions, and so on. For example, we can find many incomplete cars in Kitty dataset, and many incomplete chairs and tables in ScanNet dataset. Point cloud completion aims to recover complete shapes, 3D, based on its partially observed parts, 2.5D. In this work, we mainly focus on inferring complete point clouds conditioned on partial inputs. Therefore, 3D shape completion is expected to recover plausible yet fine-grained complete shapes by learning relational structure properties, such as geometrical symmetries, regular arrangements, and surface smoothness, which existing methods fail to capture. We propose VRCNet, shown in Figure A, and it consists of two consecutive subnetworks: first, probabilistic modeling, PMNet, and second, relational enhancement, RENet. As shown in Figure B, VRCNet can generate better shape details. In Figure C, given different incomplete point clouds, VRCNet can generate different reasonable complete point clouds. The first subnetwork PMNet has two parallel paths, the upper reconstruction path and the lower completion path. The reconstruction path is only used in training, and the completion path generates a coarse complete point cloud based on the encoded distribution and global features. The two paths use similar variational encoder-decoder architectures. Hence, we can formulate their training loss by these equations, respectively. Subsequently, our RENet adaptively exploits relational structure properties to predict the fine complete point cloud. We propose many novel modules for adaptively learning multi-scale point features. PSA uses self-attention to adaptively aggregate neighboring point features. PSK has multiple parallel PSA modules with different scales, which can adjust receptive fields for adaptively fusing multi-scale point features. By adding a residual link, we construct the RPSK module, which is a basic building block for RENet. With the proposed point feature learning modules, we design the RENet, which follows a hierarchical encoder-decoder architecture. After obtaining the dense point features, we can use EFE module to preform upsampling. The training loss has two categories, KL divergence and chamfer distance. Our overall training loss has three terms: reconstruction loss, coarse completion loss, and fine completion loss. Besides, we construct a large-scale multi-view partial point cloud dataset, the MVP dataset. For each complete CAD model, we generate different partial point clouds by randomly selecting 26 uniformly distributed camera poses. Furthermore, we set a high resolution to obtain rendered partial point clouds with good qualities. As for complete point clouds, we use Poisson disk sampling, which can generate smoother 3D surfaces than uniformly sampling. Here, we see the comparison between partial point clouds rendered by a low resolution and a high resolution. We also show the qualitative comparisons between complete point clouds sampled by uniform sampling and Poisson disk sampling. Comparing to previous benchmark datasets, MVP mainly has three advantages. First, diversity and uniform views. Second, large scale and better qualities. Third, more categories. The MVP dataset can also be used in other tasks, such as retrieval, classification, and registration. VRCNet achieves the best performance on the MVP dataset. Qualitative results show that VRCNet can better predict local shape details by learning relational structures. VRCNet also achieves the best performance on the completion 3D dataset. For real scanned point clouds, VRCNet can also generate impressive complete shapes by learning and predicting shape symmetries. In conclusion, we propose a comprehensive framework for point cloud completion in this paper. We design many novel and powerful point cloud learning modules. We establish the MVP dataset. Thank you for attention.